Hello and welcome. Thanks for all the people that subscribed to my channel and followed me. I really appreciate that. I've got like 30 something subscribers in the past 1 or 2 months. So this is great. I appreciate that. In this video, I'm going to talk about parallel processing. It's just an example of using an application or a system called portable batch system. I'm looking at my screen here. Portable batch system. And I use this to run multiple program or to run a program multiple times on different machines and then collect the results. So I use it for my NS3 simulations, but I could also use it for MATLAB. I used it for to run MATLAB code that I got from a friend, one of our colleagues. Anyways, first of all, what is portable batch system? It's the name of computer software that performs job scheduling. Its primary task is to allocate computational tasks. Basically, what I do with it is I run a program with different parameters on multiple machines at once. And this is provided by the cluster computing in my university in the United States. Now, if you look up portable batch system, basically do a search at .edu, you'll find out that a lot of American universities have that. You can also try to look it up in .ac.uk, and you find a lot of British universities. You could just try at ac.in, and you could find that portable batch system is also used in Indian universities. So it's used in many universities around the world. And if you have PBS or cluster computing in your, or supercomputing in your university or your work, because some jobs do that, chances are they're using PBS, portable batch system. So I have an example here. I'm logged into our cluster. It's called Palmetto cluster. I like to give my console prompt a good color to indicate that I'm in browsing university. I have a session with the university computer rather than if I look at my other here, Ubuntu, I know that I am on my local machine so that I don't accidentally exit from the university's system, because I need to do verification, have an email, have a second factor authentication. So I don't want to do that. All right. So I have NS3 here, and basically I could run it waf -run -run whatever. And this runs it once. And I don't like that because I have to wait for it to run and finish, and then I do it again. Now, this is called the login 001 node. Basically, what we have here is an entry point from which we could submit jobs. A job can be interactive. We do submit a job, q sub -i, and that basically is like shell login. So I log into a certain machine, it gives me node 0088. Basically, I'm now on a different machine. The file system is shared. So my NS3 directory has the same files regardless. Let me quit this. Let me try, exit. Good thing I didn't exit out of the cluster. Okay, let me do q sub -i. And then there is L -L, I think. Is that how it goes? Equals select -L. Yeah, I think it's -L select equal 1. And memory, let me get a different machine with 64 gigabyte, less than or equal 15 gigabyte of RAM. Single core jobs. Okay. So I could do n CPUs equal 8, and it will give me, a machine, a different machine than the first one, because this one probably have more memory. I don't need a lot of memory. I'll just exit this one. And same thing, can access my files. Now here's where the magic is. QSub here basically submits a job. So when I do -I, I'm doing an interactive STDN job. So it's through, basically it's like a shell login. It assigns me the machine that meets my criteria. There is a lot of criteria listed on the university's website, but what I do is I submit a different job, which is in a PBS script. So I'm going to go to my PBS jobs directory, and I have NS3 parallel. It's what I have my script. Now, if I go into this script, first, this is how it goes. This is our special comment that starts with PBS. The name of the job is NS3_CACC, Cooperative Adaptive Cruise Control. The output file, I want it to be output-ns3.txt. This is the output from multiple tasks or runs or whatever you call it, consolidated into one file. Then I'm going to specify the resources. So I'm gonna say select 32. So 32 in this sense is 32 separate machines or nodes. Each one of these should at least have, or I should be scheduled 8 CPUs or 8 cores. And each one should give me 8 GB of RAM. The wall time of the job is 6 hours. So this is 6 hours. I want it to at least last for, or at most last for 6 hours. I have to specify a time, otherwise the default will be 30 minutes. So if my simulation ends within 20 minutes, it will basically release the resources back to the cluster. I have here an option -M, which is email, and ABE. A is for if the job was aborted, B if it began execution, and E is when it ends, right? So why do I have aborted? If there is an error, it will send me that it terminated or there is an error. B, it indicates whether the job has actually started, because sometimes it gets queued. For example, if I specify 24 hours and I try to reserve 64 machines, it will tell me, okay, I'll do that in a bit, okay? Maybe depending on how the scheduler works. And basically, our system has basically a program called module, and you add GNU parallel. So GNU parallel is what I will use to run multiple processes at the same time. And basically, I have here an input file, ccac-inputs. So all my experiments are in this file. Let's see that file. Vim PBS CICC inputs. Let me make this a little smaller. Have to reopen it. No, wait, why doesn't it show it properly? Anyways, every line here is the parameters that I pass to my NS3 program, --n10, mode, some values, basically parameters, command line arguments. And to run my NS3 programs, I actually have let me go back to bigger font. It's the other way around. Then CACC parallel, right? So basically, cat, my input file, which is this one, cat will print things to the screen. So line by line, we got, every line has a set of inputs, a new set of inputs. And we feed this to GNU parallel, GNU parallel. I'm specifying that I want 4 jobs. So for each node, I want 4 jobs to run at the same time, right? I have to specify this SSH login file, PBS node file, although this is, you don't have to define this. And then what to do in each machine. So what do I do in each machine? I basically change directory into my NS3 root directory and echo hello from host name. I use this for debugging. So if a machine caused a problem, I can report it to the administrator. And I did just that once. And then the semicolon in Unix, it means it will be in sequence. So this, followed by this, followed by this script is a Python script. And this Python script, I created it to run NS3 programs. It's just easier to pass it like that. And whatever between these curly braces is the line or the set of arguments. Now, this CICC inputs file, I create that with a Python script. So I'll just modify it because I need to run another set of experiments. All right, so I have it under experiment maker, make experiment, cd, yeah, make experiment. So this is a Python code. As you can see, I used it to make a MATLAB, basically. For the MATLAB run, it calls this function, changes into directory and calls this function with these inputs and then exits after MATLAB ends. So this CICC simulation was a MATLAB code. Anyway, I have make NS3 here, and it sets some parameters. It creates like 16,000 different parameters. I could, and I'm running my experiment. I want my experiment here to have a different setup. I don't like this. Here, LiDAR, I want to say noisy sensor. Okay, if I do make experiment, you can see it creates all these files, all these, input, list of inputs, varying different parameters. So with noisy sensor. So all I need to do now, so let me see how many. So I have 28,000 different experiments in this run. Now, I am going to output this to PBS CICC inputs. Basically, this redirects whatever output of this program to this file. And we run it. Now, I am ready to get running. So let me first check my NS3 program. My NS3 installation. If I do R, which runs the last program, yeah, so it runs CICC experiments. Let me, on another window that you don't see, I will go to my Gmail and I will go to my university access. All right. Okay, now we run it. I need to submit the task from the login node because it basically does the scheduling and whatnot. So let me exit this session and I'm gonna go to PBS job, parallel, NS3 parallel. Now, this is different than the parallelization with the MPI or something like that. So I'm running different instances of the program. To submit it, I have this CICC here, vim CICC parallel. I will submit this task. So I'll submit this to the parallel cluster. But before I do that, let me just verify my input file. So this is my input file. So I'm using noisy sensor. So I have a thing where I measure the distance. One was perfect sensor. Basically, I get the exact same measurement that NS3 gives me. And one is noisy sensor, where I add some noise, like 10 centimeters or something like that, just to simulate how an actual distance sensor might work. It might actually give some noise. So this is for the noisy setup. So I will quit this. Oh, that's a capital Q. And there's something called qstat-u, my username. I have no jobs submitted. So I'm going to go qsub CACC parallel. Now this submits the job to the cluster, to the super high computing cluster. And so what it does, it sees, okay, I chose 32 different machines. It will send, it will organize it basically. It will schedule everything. As you can see, the script for the PBS is very short. And so we press enter now. And what do we get? It's told me that, gave me a job ID, right? If I go to qstat-u, my username, we can see that it gave me a session ID, the queue. So in our university, we have a tiny queue, a medium queue, depending on how big your job is. So what I requested is 256 gigabyte of RAM. So 32 times 8, because I said 8 gigabyte per machine. That's 256 gigabytes. That's my wall time is 6 hours. I don't know what this is. I think this might be TSK. No idea. Maybe this is number of cores. No idea. Session ID and whatnot. So I can check this. I got an email saying that this job, which is 8608393, has begun. As you can see, it is running. If it's not running, it will say queue. It's queued. Anyways, you read the documentation for that, you get what I mean. And now the instruction is to not use this login machine for processing and running programs. Okay? You could get a warning, you could get your jobs or your programs shut down. And so I could go and do, so this is a machine designed just to submit the tasks, the parallel task. I'm gonna go qsub-i, it will give me another task. It's interactive. And as you can see here, I could do, what can I do? I could do qstat-u, forgot my username. As you can see, I have 2 jobs now. One is this ns3-_CACC, which is this big job. And the other one is stdn. It's basically from standard input, which is this thing, what I'm typing. And actually it gives me 1 gigabyte of RAM. It's just a small thing. So I use this to basically copy files and do stuff like that. Once it's done, I'll get an email. So I could just go and have some food and, drink some coffee till it's finished. And basically, the last time I ran this, when was the last time I ran it? May 17. So let me see this. Output. Yeah, this will be a huge file. So I'll just output this file. The text will print everything that was printed to std out. And in the end, it has, so this file is the output file that gets generated. It's runs from every program. So its script is running NS3. This is the typical thing. And I have simulation parameters. This is what I print to the screen. I print it with color. Anyway, so at the end, it generates a report. This is the memory I use, the number of CPUs I use, the wall time. And this is the actual wall time. It took 23 minutes to run 28,000 experiments. You can't run that on your local machine within such a short time. Anyways, that's about PBS. Thank you very much. I hope you find this useful. Check your university, your job, if you have some high computation, high performance computing center where they have clusters, a cluster of computers where you can run many experiments at one time. I just demonstrated what we use in our school. Thank you. Have a nice day.